topic. As you know, we offer this free webinar. We're trying to do monthly to make sure that we can cover the topics that we need to cover. So I'll just do some logistics and then I'll hand it over to David Vivanco. I think you all know David well. So you're going to get, those of you who would like to get 1 hour of professional development hours, PDH hour, you will get it. Also, the slides, a PDF of the slides would be posted on the SPTC website. And also this presentation is going to be recorded. We hope that you all agree with that, and the recording will be posted as well, so that in case you are not able to actually, some may be not able to attend, or some may not have enough time to ask questions and so on, or follow through everything. Those materials will be available. And in any topic that you want to have future webinar, please let us know, and whatever speaker that you would like to see deliver that topic, will be glad, SPTC will be glad to host it. I think this is a wonderful opportunity for all of us, and I'm a professional PE, so I think I need my PDH as well. So that's something, it's a free PDH, and I think very helpful as well. So with that introduction, I'm actually going to the logistics. One more thing regarding the questions, I think David is going to share with you more specifics, and also but in any case, I'm not going to take any more time. So I want to thank you again for your presence. We know that you all have other options to do, but we greatly appreciate the fact that you took opportunity to time out of your busy schedule to attend this virtual event. So with that, and all of you know, I believe David Vivanco, he is he's the lead person, the branch manager at Oklahoma Department of Transportation, doing in the asphalt area. It is indeed a pleasure, and David joined ODOT. Actually, I think he was at ODOT before, then he left for his PhD. He came back. So we're really very pleased to have David back in Oklahoma, because we need all of his ideas, to move this particular topic forward and other things. So with that, David, I'll turn it, to you to introduce our speaker and to, for the rest of this event. Thank you, David, and thank you, Dr. Fujie Zhou.
Thank you, Dr. Zaman. Well, good evening, everyone. Welcome to the Elements of Balanced Mix Design webinar. Thank you, Dr. Zaman, for the introduction. And I just want to mention that, well, this is a very important topic for ODOT. We've been working on BMD since 2018. We're continuing to make progress with its implementation. We currently have a BMD special provision that will be used in 4 pilot projects this year. And we expect to have at least 8 implementation projects next year. So we're very excited for the opportunities that BMD will bring to the state and to the asphalt industry as a whole. I'll be responsible for moderating this presentation today. With the questions, well, you can type your questions and comments in the chat box. You can address those to me. And we will have some time at the end of the presentation to go over, those questions and over the discussions. Our speaker today is Dr. Fujie Zhou. Dr. Zhou is a research engineer with the Texas A&M Transportation Institute. And he has over 30 years of research experience in asphalt binder mixtures, mechanistic empirical design, pavement rehabilitation, and automated lab tests. He has published more than 50 journal articles and more than 25 conference papers, including many research projects sponsored by NCHRP, the Texas, and other DOTs, as well as the private industry. He pretty much originated balance mix design concept in 2005. Later, Dr. Zhou developed the Texas ME payment design program, the ideal cracking test, and the ideal routing test standards, and is currently working on this automated testing. Additionally, he is a 3-time recipient for the AAPT Best Paper Emmons Award. So as you may see, he has a wealth of knowledge. So we're very happy to have him here today. Well, without any further delay, I'm glad to welcome our guest speaker, Dr. Zhou.
Thank you, David. Thank you, Dr. Zeman. And it's a great opportunity to present what we have been done in Texas, specifically in TTI, for the topic balance mix design. Let me start sharing my screen. So I'm assuming you see the right screen. Is that right? Is the presentation mode?
We see presentation mode, yes.
All right, that's great.
I mean, no, we see the presenters mode.
All right. How about this?
Yeah, there you go.
All right, great. So again, the topic today we're going to talk about is the balance mix design. I just gave a different name. It's called the elements of a balance mix design. So here's the outline of this presentation. Give a brief introduction, talk about why we do this study, why we need a balance mix design. Then we go through detailed zoom in, talk about balance mix design, specifically on three areas: performance test, the aging protocols, and the performance criteria. And the last two topic is how can we implement the balance mix design during the QC/QA at the plant production. And last but not the least, how can we improve the cracking resistance? I think that's the most difficult issue we are facing. So at the end of this presentation, we give a summary and the conclusion. So we have been, I think in the last 3 or 4 decades, our payment distress is swinging from left to right. And before the SHARP program in the late 1980s, routing was a big issue. That's how the strategic highway research program was started. And right after the SHARP program in early 1990s, people started to use the SilverPave volumetric design. And then we had issues with moisture damage. So that's in the 1990s, early of 1990s. So 1 decade after SHARP program in the 2000s, and the cracking became the big issue. And talking about the cracking, it's not just one type of cracking. Actually, there are 4 different types of cracking. The refractive cracking associated with asphalt overlays, the fatigue cracking associated with most of, for new pavement construction. We also have top-down cracking in most of the cases for very thick pavement, longitudinal, in the well pass area. And last but not least, thermal cracking. I think in Oklahoma, in the northern state, they have lots of, thermal cracking. For example, in Minnesota, Wisconsin, or those areas. So what really led to different type of pavement stresses, swinging from rotting to cracking? So what's really led those issues? In the surface, people maybe say we use, the binder. We switch binder from AC20 to PG76-22. The binder becomes stiffer, so we eliminate the rotting issue. but to the binder is too stiff and cause cracking issue. Another thing people may say, oh, well, binder content is much less than 30 years ago. That's cause cracking issue. That could be the reason. And we are using lots of coarse gradation. That's led to the moisture damage issue. And we have been using recycled materials in the last 10, 15 years. And another thing, potentially the binder quality. But all this are reasons, but that's the root problem. Still is the limitations of our current silver paper mix design method. So in order to truly solve this problem, we have to look into the root problem and solve the issues from the root. So what's the problem with the current silver paper volumetric design? We all know volumetrics like air void, VMA, VFA, all these are very important for payment performance. But at the same time, we all know volumetrics alone are not enough. So there are here at least several limitations with the current silver paper volumetric design. The first one, when we talk about binder quality, I think in every state, they may using PG6 format 22 or PG70 or PG76 are different, performance grade binders. The problem is with the same PG, for example, if you may have 2 or 3 PG6 format -22. When you go through the volumetric design, they may give you exactly the same asphalt content, but the binder quality itself, the binder itself may significantly different. We're going to show you some example at later time. They have same PG, but they potentially have completely different cracking resistance. The second thing is about we are using reclaimed asphalt pavement or ramp or recycled asphalt shingles, rejuvenators. How these things blend together with wooden binder. And the recycled binder is 100% available, 50%, 75%, its availability is one thing. Another thing is how these binders, diffusion and into the wooden binder, how these things work together, we really don't know. But the volumetric design assume that's 100% blending. And another thing is a bulk specific gravity. That could lead lots of errors when calculate VMA. So that's in terms the ramp and RAS rejuvenator. All these issues can cause some errors in terms of volumetrics. And another thing is about other additives, warm mix additives. Most recently, people are using plastic, tire rubbers, and fibers, and maybe some new additives in the near future. So the current volumetric system really cannot consider in all these factors well enough to address them. So really ultimate solution is balanced mix design. We consider volumetrics, but also we are using practical performance tests to characterize the mix in terms of rotting resistance, cracking resistance, and the moisture damage. So that's why we really need the balanced mix design to employing performance tests to characterize the mix. It's not just volumetric alone. So that's the balanced mix design is about. So when we talk about balanced mix design, what's the balanced mix design include? What's their essential component? But again, a balanced mix design has been discussed in the last 10 years, but the development of balanced mix design is far beyond. Actually, we started the balanced mix design, the concept, and started in 2005. We published the first paper in 2007. And back then, we used the two tests. One is the Hamburg wheel tracking test, and another one is the Texas overlay tester. So this is the two test equipment just showing here. And we came up with this balanced mix design concept. And in order for a mix to perform well in the field, they must have adequate rotting resistance, moisture damage resistance, and cracking resistance. So simply put, this concept in one graph. You have multiple asphalt binder contents, like the green, the red line, this line, that's the cracking resistance. With asphalt content, increasing asphalt content, your cracking resistance getting better and better. And this green line corresponding to rod depths from the Hamburg wheel tracking test. Most of states are still using the half-inch as a criteria. So the blue line, if you cross this line, the intersection with this green line, that's the Hamburg wheel tracking test result. The more asphalt content you add to the mix, you get the higher rod depth. So this intersection and coming down to this asphalt content, and this is the maximum asphalt content that you can add to the mix without causing rotting problem. So in terms of the cracking, we have the minimum asphalt content in order to meet the cracking resistance. So this yellow zone we call balanced zone. That's how we call balanced rotting and the cracking requirement here. So that's the basic balanced mix design concept here. So zoom into this balanced mix design. Actually really have three major components when we're talking about balanced mix design. And the first one is the performance test. And I specifically highlight here is the practical performance test. And the major difference, and if you look at this back in 2007 or 2005, and this is the rotting test, Hamburg test. This is the overlay test we have been developing for decades. And this test, compared to back to the super pave simple shearing test, it's much simpler compared to that. So that means it's much more practical for DOTs and the asphalt industry to adopt, to use. So that's extremely important. And it's not just simply a performance test. It must be practical. We're talking about the cracking test, talking about rotting test, talking about moisture damage. So we have to consider all three of them. Another aspect is aging protocol, because we all know of asphalt mixes age. Their mixed performance is aged as well, changing with aging. And the more you age in the mix and you have better rotting resistance, the poor cracking resistance. So we have to, talk about what kind of short-term aging protocol we should use. Do we need to consider mid-term aging for asphalt overlays? When we talk about mid-term aging, this is a terminology we coined several years ago, specifically for asphalt overlays, because asphalt overlay, normally we see, 4 years, maybe 3 years, depending on how thick your overlay, and you see lots of cracking. That's probably, already you finish your aging in terms of, performance. So that's why we came up a mid-term aging. For the long-term aging, specifically for the new pavement, because the new pavement design, we talk about 15, 18, 20 years, you have to consider long-term aging. So when we have this performance test, we have aging protocol, then we can talk about the criteria and for acceptance criteria. So if you use Hamburg test, we all know most of people still using half-inch, and for different PG binders, for example, for 76 MER22, and is 20,000 passes, half-inch maximum run depth. So that's, considering climate and the pavement structure and traffic. So all this has influence on the criteria. So let's zoom in for each one by one. the first one. Let's talk about the cracking test. I'm listing here a 9 type of different cracking tests. And you probably sometimes already heard different type of cracking tests. I just refresh your memory. I break into the cracking test into monotonic cracking test and the repeat loading cracking test. And in terms of the monotonic cracking test, I'm listing here 5 of them. Like the disc-shaped compact tension test. This has been used by Minnesota DOT, and the semicircular bending at low temperature. As far as I know, this test nobody use it for except some research has not been adopted by any DOT. This is another semicircular bend test developed by Louisiana Transportation Research Center by Dr. Louis, and the Louisiana DOT is using it. And this IFIT test developed by Professor Imad Arkady is being used by Illinois DOT, and ideal cracking test. So this the monotonic test. And this is repeat load test, a bending beam fatigue test, and the Texas overlay test, the asphalt mixture performance test, a cyclic fatigue test, and there's another one is the IDT University of Florida test method. For each test, and under NCHRP 9-57, and on this website, they have the videos. You can go this website, look into each test. We produced 10 test videos over there. So this show you these 3 monotonic SCB tests. You look at this different loading frame, but the specimen all although there are specimen size a little bit different, but they're all semicircular, and have a specimen chopped from the middle, from the middle, get 2 semicircular specimens. Some specimen you need a notch. All the specimens need a notch in the middle of this specimen. So this another 2 monotonic tests. This is a DCT test. You have to drill 2 holes with the specimen, and another big notch, and lots of gluing work as well. This is an ideal CT test. I'm going to have a few 4 minutes video to talk about this test next few slides. And talking about the repeated load test, this is the beam fatigue test. It's a long beam, 15-inch long beam. It's very difficult to make the beam specimen. And this is a Texas overlay tester. You have to cut, make tall specimens, chop from the top and bottom, and chop in the left and right to get the small specimen for overlay test. And for overlay test, you have to glue it. And you have to make sure the glue is dry before you test it. And this is the Florida IDT test. You have lots of instrumentation. Again, this is the AMPT cyclic fatigue test. You have to make larger specimen and core and dry and glue the instrument. All this piece of is a very tedious process to run this test. And so you may ask which one is the most practical test and for DOT and to use. So I'm going to show you a video talking about the ideal cracking test. I may be biased because I developed this test, but it's not just my own opinion. I have somebody from other DOTs from industry. They have talking about what they see this test.
The audio, it's I don't think we can hear the video. Maybe you can go close with that.
Fuji, could you check your sound, Fuji, because this we cannot see we cannot hear.
I'm sorry.
Yeah, there is no sound.
Oh, no sound.
Yeah. On the video.
On the video, yeah. How can we give the sound, make the sounds available? Let's okay, let me take my phone. That may help. Can you hear now?
In the end, for our criteria and our needs at the time, the ideal
Yes, we
CT
can hear now.
as our preferred test to start implementing.
To do performance testing, it would be different than just going on volumetrics. And so we wanted to try to find a test that would be simple, fast, and something that would be repeatable. A test that you could train anyone on it and it would be easy to train someone. We do a lot of different performance testing, but I think the ideal CT is really the one that right now we're envisioning the most with the ideal CT for cracking.
A great index test, whether I'm using it for private clients, whether I'm using it for the massive amount of payments we have with agency DOT work, or if I'm using it for product innovation. It hits all points with me.
We wanted something that's duplicatable and easy to use, that we can get it in the contractor's hands and at a minimal cost. We have come and settled on using the ideal CT. There's no cuts, there's no notches, and we're getting solid numbers in the things that we've been running in the tests so far.
Quite frankly, all the data we've looked at and everyone we've talked to, the CT index, it holds equal levels of strength in its analysis, if not better, than many of the other tests out there without any of the additional work and fabrication. And we really like the fact that the 62 millimeter specimen takes a lot less training because the lab's already used to that. There is an additional level of cutting and notching and coring, and so there's safety benefits as well.
No test is perfect, and while this one is still an index test, and we have to understand it's an index, it is spot on with what industry needs to be able to provide a quick test to understand if I'm going in the right or wrong direction in order to build a pavement that should have less cracking.
There's a lot of tests out there, and they're great for research, and they may be great in design when you have enough time, but getting something that, we can put in a contractor's lab and test pretty much real time is game changer.
If you'd like to see the complete video of the ideal CT test being performed, you can visit the TRB webpage, Idea Project 195, or you can click the YouTube link shown below. For more information or questions about Ideal CT, please email or call the original.
All right, I think, let me adjust. All right, I think cracking test is enough. Let's move to the rotting test. Right now I'm listing here another 9 rotting tests. Again, it could be a monotonic test and repeated load test here. So here show you several 4 monotonic tests. The left one is Marshall test. Let's see, in the history, many states have used this test. And the Vim stability test has been used in the West Coast, many states. I think Nevada may still using this test. And this one is a high temperature IDT test. This is the most recent one. This way developed ideal rotting test, ideal RT. This the major difference. You look at this test and this test. This have one supporting bar at the bottom, mainly measuring the tension, and this have two supporting at the bottom here, and the top in loading here. You have generating the shearing stress because the rotting is really caused by shearing. And this give you the pictures for repeated load test. This is a simple shear test developed by UC Berkeley, Professor Morgan Smith. And this, most people using the Hamburg wave tracking test. This is some states using the APA. This is a flow number test. So this kind of a rotting test. And I'm highlighting here with the Hamburg wave tracking test, APA, and the high temperature IDT, ideal RT. This is the 4 tests for rotting tests some states have been looking into, some states have been using for years. Talk about moisture damage. Mainly is either people using Hamburg test or the tensile strength ratio as an indicator of moisture damage. So these are 2 options. So many states are using Hamburg for characterizing both rotting and the moisture damage. That's why Hamburg is a pretty popular test. I think that's enough for in terms of the performance test. Let's move to the aging part, because aging is so important. We all know the field, the mixed aging process is during the production, transport, and the placement. This is the type of period we call short-term aging after paving on the roads, and like this one, and you're going to serve for 10 years, 20 years, 5 years. That's we call long-term aging. So for any mix design, and we need to consider both short-term aging and the long-term aging, because the mix rotting, the cracking resistance varying with age, and specifically in opposite way. And for the rotting resistance, like this blue line, they're getting better and better. And for the cracking resistance, this orange line getting worse and worse. So that's why for the rotting, the short-term aging is critical. For cracking, long-term aging is critical. So we have to consider both short-term and the long-term. So in terms of the aging protocol, we have to consider how long we're going to aging the loose mix in the oven, what the temperature should we use, how thick our loose mix should be. So because another thing why this is so important for the aging, because without specifying the aging protocol, we actually can make the mix pass any criteria you set. Because again, if I want passing my rotting criteria, I can cook my mix a little bit longer in the oven. If I want passing the cracking criteria, I probably, after I mix it, I can directly compact the specimen and test it. So that's really the aging is extremely critical for performance tests, specifically for the criteria we're going to set. In the literature, I have all sorts of aging protocols, and you can see multiple protocols, and but which one can be practically used. So that's how we studied different aging protocols. We published several papers, 2 papers in WAPT conference 2021 to 2022, talking about the midterm aging as for the overlays, and another long-term aging for new pavement construction. Basically, this is what we recommend for short-term aging, and for the temperature, going to compaction temperature, and the duration for aging loose mix in the oven is 2 hours. How thick the loose mix is, 1.5 to 2 inch. Really don't want too thin or too thick. So that's what we recommend for short-term aging. And for the midterm aging, the only differences is the aging temperature, 100 degrees Celsius, and the duration is 20 hours, and the loose mix thickness still 1.5 to 2 inch. For the long-term aging, we increase another 10 degrees Celsius. If you look here, we have a map for the national map. For long-term aging, most of them, say in the south areas, in Texas, Louisiana, Florida, and this 120. In the middle of the area is 110. In Oklahoma, it's 110. And at the above here, around, 100, 105, something like that. So this, to simplify the aging temperature and the time and thickness. Why we choose 20 hours? Because 20 hours is, we think is corresponding to the binder PV aging 20 hours, has been using 3 or 4 decades. And that means people, it's practical enough, people have been using it, not changed yet. And also give people flexibility to work within the working hours window. So that's how we choose 20 hours. After you choose the cracking test, the rotting test, the moisture damage test, you pick up your aging protocol, then you can really need acceptance criteria to have mixed design. We need acceptance criteria for rotting, for cracking, moisture damage. There are 5 different ways to establish acceptance criteria. The easiest way is just using your neighbor state's criteria, or like Oklahoma, are using Texas, or Arkansas, and or any other state you think is can represent your state. And the second thing is you can establish a correlation with the existing performance test and associated criteria. If it's a new test, you can, through the correlation based on existing test criteria, you can get, new test criteria. The third is benchmarking. And run the test your most often used mixes, then you can set up a criteria. The number 4, the field test sections, build the field test sections, maintain performance, and then you can, establish the criteria based on the field performance. The number 5 is based on performance simulation. If you already have your Texas, I'm sorry, not Texas ME, is a national ME, and you can run different types of scenarios and characterize your mixes, and then your performance, you can establish some criteria as well. I'm presenting you 3 practical ways to establish the criteria. Here, this is how we recommend ideal RT test criteria based on the correlation with the Hamburg wheel tracking test. So the y-axis, that's the RT index, x-axis is the Hamburg wheel tracking data. Based on this correlation, we recommend for 6-4-22 or 6-4-28 binders, the minimum RT index is 60. For PG76, minimum is 75, PG70 in the middle here. And the Taiwan benchmarking, you can, currently TTI is working with Arizona DOT to benchmarking their mixes. So you just, choose the typical mixes, perform the test, analyze the distribution. For example, this is kind of a distribution. For the CT index, it's a cumulative, distribution. If I set up my passing, I want my 70% mixes passing. So that's how we come up with the criteria. CT index is 55. If you want 50% passing, you probably talk about 65 or 70 here. So that's how you can choose based on the lab test results, draw your histogram, that's graph, and you come up with this cumulative distribution. You pick up a passing percentage, you can get your CT index criteria. And another example is field performance test section. I'm using the SPS 10 in Oklahoma. That's wall mix test sections. And over there, I have 5 test sections over there. This overlay ideal CT test results. This observed refractive cracking after 40 months of service. If you want to pick up 20% refractive cracking, and you get the criteria 70. That's ideal CT index 70. That's another way establish the field performance and your CT index number, draw a curve, then you pick up the minimum your tolerance, you get your CT index criteria. So how can we put everything together? This is the BMD, basically equal to SuperPave, current SuperPave volumetric design, plus 2 performance tests with short-term aging. I'm picking up here Hamburg wheel tracking test, ideal CT. Basically, this is the basic process. Everybody very familiar. And the volumetric design, you pick up a 96 density, you get a 1 binder content, and then you run your performance test. Are we passing my Hamburg test and the ideal CT test? If performance passed, then you got to go to your Java mix formula. And if not, you go back, you can change your binder, change your gradation, and reduce your ramp percentage, and I'll use rejuvenator and do it again. That's the most of a common framework people are using right now. So after you have this Java mix formula, then the next thing going to field production. So how can we make sure our field production is still balanced? So that's why we talk about very important for QC QA. And the current practice, we're looking at the rise and the lab mode density. And we also look at as for the content, the gradation from ignition oven test. But we do have some concerns. The reality is the performance tests are used in the balance mix design, but none in the QC and the QA process most of the time. The reason is too much work and short of workforce and too long running time. So what's the consequence? The consequence is what is produced at the end for the plant may be significantly different from what was designed in the lab. That's what we really don't want to see. So another thing is if during the production they switch binder and you potentially can get a completely different mix, but you still have the same binder content, same volumetric, but performance could be completely different. So how can we, address these issues? Too much work and we don't have workforce and too long running time. So we, that's how we, in the last several years, we put a huge effort to develop this automation test. So automation can help solve the workforce constraints, increasing productivity, improve accuracy by removing human errors. So that's what we're using robot to accompany do the test. So when we talk about robot do the test, what kind of tests we really need? I'm listing here the 4 essential lab tests: bulk specific gravity or air void, and IDT test, IDT strength or high temperature IDT, or ideal RT test, ideal rotting test. So that's what we are focused in for the automation. The next slide, I'm going to show you a 2-minute video. You can see the process of this automation. So you put one sample on this conveyor belt, and the robot picks it up and then measure the air void. And this one, right now, they're measuring the dry weight, and then they're going to measure the weight, sample weight in the water. As they are coming up and put specimen into the basket, lower it down, and let it stay over there, say 4 minutes based on the test procedure. But for this video, we just pick it up very quickly to save people's time. So the next thing we're going to do is the SSD to dry the specimens, and so after this SSD drying, and then we get another weight is SSD weight, and then we put the sample on this little carrier. If you don't want to do any further tests, you can take your sample away. So finish that test, get another specimen. This one going to run the ideal cracking test or IDT indirect tensor strength test. You can see the loading frame and crashing this specimen. And then we're going to move the specimen out of this loading frame and into the trash can. So this is the second one. And if you see that previous specimen, after we get a sample, we directly test it. But this one, we want conditioning it. And because in order to make the test temperature be accurate, we want conditioning in the water bath and 25 degrees Celsius. And then we have a quick dry. We really don't want the water dripping everywhere. So quick dry the specimen, they picked it up and run and ideal CT test again. So the same thing, we can run the ideal RT test, and but this one they just showing this ideal CT test again. So trash it again. So after finishing all these tests, you're going to see the test results summary page, and show all the curves. And the left one, this is the CT test, this is the RT test, and all the sample information. All this data can be sent into your email box and to look at. So the beauty is everything is automatic without human intervention. So let's talking about what's the issues, our most common mixes right now. Is cracking. We all know we have cracking issues. This cracking is controlled by many mixed components aging. So I would say in order to get a better cracking resistance, you have to work on all these areas. But I want to say, again, as I mentioned, aging is a significant factor for cracking resistance. And specifically here, I have 13 mixes on this ideal CT test result. All these mixes has same gradation. I'm sorry. Some of the mixes have same gradation, exactly same gradation, same asphalt content. The only difference is binder type. The same PG, even same PG. You're going to see, again, different mixes aged completely different. And the binder source, again, the source, these two mixes have the same, again, same PG and same asphalt content, same gradation, same aggregate, only different source. You can see the age is completely different. Same thing for another two mixes. This is PG 64-28. This is 64-22. And not just a binder source, and binder absorption has another significant impact for poor cracking resistance. The low absorptive aggregates always have better cracking resistance. And the binder content, we all know binder content. We increase the binder content, you'll significantly improve your cracking resistance. So maybe this is a very effective way to improve your crack resistance. Another thing is the binder grade, 64 versus 34 minus 34. So 64-22, 64-28, 64-34. Apparently, you change your lower end of PG, you can significantly improve your cracking resistance. And another thing I just want to warn everyone, you increasing your binder grade at the higher end or using polymer modification, there may not guarantee improve your crack resistance. So this is from Casey Nash. He's from Main Duty, from one of his slides. And he said the field tests show that all PMA in general have improved the rotting resistance. But in terms of the cracking, polymer that used 80 to 100 pin-based binder in these test sections have more cracking than the control section. So he cited this from a TRB publication. So another example, this is from NCAT test track back in 64-22 versus 76-22. And in the 2006, exactly N1 and A2, exactly same payment structure, same asphalt content. And the only difference is from changing 64-22 from 76-22. But if you look at, their cracking, fatigue cracking, basically the same, basically the same. So that's really, remind us there's no guarantee we really can improve cracking resistance when we're using 6422 tend to 7622. But that's not mean your 7622 has no benefit. They do have benefit for writing resistance and for cracking resistance, but you have to use it in a correct way. So again, to summarize it, improving crack resistance, you have to know your materials and select them properly. When you select for the binder, look for the grade, the binder source, and the content. Look for aggregate absorption. That's very important. When you're using recycled material, you need to characterize your wrap. Not all the wrap are the same. Not all plastic the same. When you choose additives, again, do your homework using rejuvenators or any other things. Not all the rejuvenators are the same. Consider mixed aging factor. If you mix aging pretty quickly, you have to look into not just short-term aging, you need to look at long-term aging. Using practical performance test and for your balance mix design and also quality control during production. And another thing we have to remember, we need to remember the contribution from pavement structure, the structural thickness. That's another very critical factor for your pavement performance, because materials sometimes improve to a certain degree is you have to go through changing your pavement thickness. And again, to address your cracking problem, may need more than just balance mix and QC/QA. You need to know your existing pavement structures as for the overlay. You need to evaluate pavement condition before your overlay. Is this 2-inch overlay is a good option for your current pavement condition? And conduct as for the overlay thickness design, consider traffic, climate, existing pavement structure. So in Texas TTI, we have a Texas as for the overlay program can be used for design pavement thickness, overlay thickness. So this come up my summary and the conclusion. The BMD is a very practical method for ensuring good performance. You have to look at the practical performance test, look for practical aging protocol, establish your criteria, acceptance criteria, and the manufacturer's impact crack resistance. As for the contents, always very critical. Also pay attention to your materials and aging. And always remember, not all the same binders, PT binders, the wraps are performed the same. Do your homework. And also another one is using the performance test for the QC/QA. Ensure what you designed is being produced in the field. With that, I thank you very much for your attention.
Well, thank you. Thank you very much, Fujie, for your presentation. Very interesting. It's a topic that it's very interesting for everybody in the different DOTs. So we'll move on to questions. I have a couple of comments here. The first one is from Tisha Reynolds. She says, R. purchased 13 Humboldt ideal CT machines, and we have a lot of problems with the machines shutting down during testing. Do you have any recommendations on that regard?
For the ideal CT machine?
Yeah.
Oh, I think the ideal CT machines on the market, all of them should work. So we have been using a hydraulic system for our research institute, but for the most of DOTs, you can even use your old Marshall press and to do the ideal CT test. I personally don't have any preference, and anyone I think should do the work, but make sure they have a pretty good the loading, recording, and the RVDT, and so that's all information I can provide.
Okay, thank you very much. I have another comment here with Kenneth Hobson. He says CT index is insensitive to specimen height.
I think we did wrongness test through NCHRP 9-57A, and the thickness height is not the big factor. You can go plus minus 2 millimeter, 62 plus minus 2 millimeter.
Yeah, I think also like the formula itself includes the area of the cross-section area, right, for calculation.
The thickness is included the calculation, is considered.
So we have another comment here with from Matias Mendez. He say, would you recommend typical ignition oven for AC content when BMD contains wrap for QCQA?
That's a great question. I think should be David's question. That's you. If you really ask me, I think really, as I emphasized during the presentation, we need to look at really need to look into is the performance test during the QC process to ensure what we produced is what we designed in the lab. That's more important than the ignition oven. Although ignition oven is always a part of the the QC process.
Yeah, I think I will add to this that we're working on pretty much answering that question here in Oklahoma, and we're trying different. We're trying ignition oven and as well automatic extraction. So we're seeing what's the difference with wrap mixes, and we're actually requiring the producers to determine the wrap binder content by extraction only, not by ignition, because we don't have the correction factors and some other issues with the ignition oven. So right now we're using only extraction when determining the wrap binder content. Another question from Ken Hobson. He said, adjusting aging protocols for WMAs.
That's another great question. I think maybe a year from now, we're going to have a clear answer. Currently, I think Oklahoma State University in Deb, he's leading a research to look into this issue, the WMA and HMA, should we change the test temperature for aging? And so I think let's have a little bit more patient, wait for some time, and based on the test results, we can make a much better scientific conclusion and our decision on that.
Yeah, I agree with that. I think actually on our special provision in Oklahoma for BMD, we are actually requiring a lower temperature for short-term aging for warm mix as well. I think we require 240 degrees for warm mix and 275 for hot mix for short-term aging. So we'll see how that goes. Another comment from Tisha from RDOT. When pulling samples of plant mix, do you age the asphalt any before compaction of ideal CTs? Should samples be brought back to compaction temperature?
That's a great question. It's a pretty technical question. In Texas, yes, that's a TxDOT required procedure. You sample from the truck and at asphalt plant, bring it into the lab, and you set up your we call compaction temperature. Stay there 2 hours. So after that, you measure your rise value, compact the sample, measure the lab mode density, and the same thing for ideal CT, for ideal RT. That's what we recommend, because the plant production, and we all know the aggregates in the big drum probably less than 2 minutes, sometimes just less than 1 minute coming out. Although the temperature pretty high, the time still the issue. and absorption, all kinds of aging doesn't happen. So that's why we always recommend still hold the mix in the compaction temperature in the oven for 2 hours.
I think we have time for one more question, and it's from S. Thomas. Will the operating temperature in the asphalt furnace remain the same, or will it be lower with BMD?
So the question is, if the temperature lower during the big drum mixing?
I think it's referring to the NCAT oven. If the temperature for that is going to be the same for ignition, or it's going to be lower.
Are you talking about ignition oven test? Or?
Yes, I think it's talking about ignition oven.
Oh, we're using the Troxler. I think that's also NCAT oven as well. We just we normally set up the temperature what the state says. We don't deviate from that. This has been settled there. We normally don't change that.
Sounds good. So those are all the questions that you're run out of time. Thank you, Dr. Zhou, for everyone in the audience for attending and for this excellent presentation. Very interesting hearing about BMD today. Yes, Katie, do you have any closing remarks?
I do not, but if you have any questions or comments, please contact us here at SPTC and we'll be happy to help you.
Sounds great. Well, thank you, everybody, and have a great rest of your day.
Thank you all. Bye-bye.